Around 400 BCE, Democritus declared that the cosmos is, quote, in reality only atoms and the void. A prophetic statement if there ever was one. It would take over 2,000 years for scientists to conclusively demonstrate that the hidden structure underlying all the things we see, steel and stars, frogs and fire, could be described in terms of fundamental, indistinguishable building blocks. Then we looked closer. Atoms themselves have a hidden structure. Electrons orbit a nuclear core, which can be further broken down into smaller structures and substructures. Protons and neutrons, quarks and gluons. Physicists worked out the abstract rules governing how these particles interact, and those rules revealed another view of the cosmos as an eruption from the froth of fundamental fields. Scientific thinkers have pursued the hidden structure of the cosmos since before there was a discipline called science. The search, if anything, is growing only more intense. Cosmologists know that there's an invisible something holding the universe together, a substance as pervasive as the pre-Einsteinian ether, and just as poorly understood. Physicists probing the paradoxes of black holes have grown convinced that there's a fundamental connection between information and the geometry of space-time, a connection that a landmark series of papers has begun to map out. And the particle itself, that fundamentally indivisible thing, the modern incarnation of Democritus's atom, may be, at its core, a physical expression of mathematical symmetries. A new map of all the particles and forces. All of nature springs from a handful of components, the fundamental particles that interact with one another in only a few different ways. In the 1970s, physicists developed a set of equations describing these particles and interactions. Together, the equations formed a succinct theory, now known as the Standard Model of particle physics. The Standard Model is missing a few puzzle pieces. Conspicuously absent are the putative particles that make up dark matter, those that convey the forces of gravity, and an explanation for the mass of neutrinos. But it provides an extremely accurate picture of almost all other observed phenomena. Yet, for a framework that encapsulates our best understanding of nature's fundamental order, the Standard Model still lacks a coherent visualization. Most attempts are too simple, or they ignore important interconnections, or are jumbled and overwhelming. This approach doesn't offer insight into the relationships between the particles. The force-carrying particles, namely the photon, which conveys the electromagnetic force, the W and Z bosons, which convey the weak force, and the gluons, which convey the strong force, are put on the same footing as the matter particles those forces act between, quarks, electrons, and their kin. Furthermore, key properties like color are left out. The law of vibration. According to this law, anything that exists in our universe, whether seen or unseen, broken down into and analyzed in its purest and most basic form, consists of pure energy or light, which resonates and exists as a vibratory frequency or pattern. Some people call this your aura, which is also the color of the magnetic field you reflect. Every thought and every feeling has its own vibration, and these vibrations find similar frequencies when another object, person, thought, or feeling give out the same vibration. That's why and how we find and connect with most like-minded people in this universe. It's because at that particular moment in time, they were on the same wavelength as us, because of a similar vibration. According to science, everything in the manifest universe is made up of packets of energy, the sizes of which are quantified by the amount of vibration and the frequency they give out. Quantum physics say that matter, when observed through a high-powered microscope, appears to be broken into tiny molecules, atoms, neutrons, electrons, and quanta, the smallest measurable particles in the universe. And it all begins in the thoughts we think. What you're feeling in the current moment determines your vibration, and subsequently, the frequency you're on. The law of correspondence. This is the law of correspondence, in so many words. The universal law of correspondence states that the principles or laws of physics that explain the physical world, energy, light, vibration, and motion have their corresponding principles in the etheric or the higher universe, that which is not material. Basically, whatever is above is like that which is below, and whatever is below is like that which is above. So if you put it into simpler terms, whatever you were thinking or feeling within is exactly what is happening outside of your mind and body, and this relates to every object, place, or person you come in contact with. If you're thinking hate, hate is what's being corresponded by you externally. And so, according to principle and by law, you must get back that same hate through a person, place, object, or circumstance. Your external life and surroundings are a reflection of what you're thinking and feeling within you. If you're feeling messed up in your head and heart, it reflects in the way you work externally, in the way you keep your work desk, or even your private home space. If you're in a calm state of mind internally, your external surroundings resonate with that sense of calm. And that's why it is humanly difficult, and sometimes even impossible, to conflict with the way we feel on the inside, because it is hard to feel happy within and act like we are angry outwardly, or feel depressed from within and act like we're absolutely fine externally. This is also the reason why, sometimes, most of what we want never manifests, because we are constantly lying and in denial about our most raw and genuine thoughts and feelings. And this corresponds with everything, from our health and jobs to more. The most famous paradox in physics nears its end. In a series of breakthrough papers, theoretical physicists have come tantalizingly close to resolving the black hole information paradox that has entranced and bedeviled them for nearly 50 years. Information, they now say with confidence, does escape a black hole. If you jump into one, you will not be gone for good. Particle by particle, the information needed to reconstitute your body will re-emerge. Most physicists have long assumed it would. That was the upshot of string theory, their leading candidate for a unified theory of nature. But the new calculations, though inspired by string theory, stand on their own, with nary a string in sight. Information gets out through the workings of gravity itself, just ordinary gravity with a single layer of quantum effects. This is a peculiar role reversal for gravity. According to Einstein's general theory of relativity, the gravity of a black hole is so intense that nothing can escape it. The more sophisticated understanding of black holes, developed by Stephen Hawking and his colleagues in the 1970s, did not question this principle. Hawking and others sought to describe matter in and around black holes using quantum theory, but they continued to describe gravity using Einstein's classical theory, a hybrid approach that physicists call semi-classical. Although the approach predicted new effects at the perimeter of the hole, the interior remained strictly sealed off. Physicists figure that Hawking had nailed the semi-classical calculation. Any further progress would have to treat gravity, too, as quantum. That is what the authors of the new studies dispute. They have found additional semi-classical effects, new gravitational configurations that Einstein's theory permits, but that Hawking did not include. Muted at first, these effects come to dominate when the black hole gets to be extremely old. The hole transforms from a hermit kingdom to a vigorously open system. Not only does information spill out, anything new that falls in is regurgitated almost immediately. The revised semi-classical theory has yet to explain how exactly the information gets out, but such has been the pace of discovery in the past 2 years that theorists already have hints of the escape mechanism. Quote, "That is the most exciting thing that has happened in this subject, I think, since Hawking," said one of the co-authors, Donald Marolf of the University of California, Santa Barbara. "It's a landmark calculation," said Ava Silverstein of Stanford University, a leading theoretical physicist who was not directly involved. You might expect the authors to celebrate, but they say they also feel let down. Had the calculation involved deep features of quantum gravity rather than a light dusting, it might have been even harder to pull off, but once that was accomplished, it would have illuminated those depths. So they worry they may have solved this one problem without achieving the broader closure they sought. Quote, "The hope was, if we could answer the question, if we could see the information coming out. In order to do that, we would have had to learn about the microscopic theory," said Jeff Pennington of the University of California, Berkeley, alluding to a fully quantum theory of gravity. What it all means is being intensely debated in Zoom calls and webinars. The work is highly mathematical and has a Rube Goldberg quality to it, stringing together one calculational trick after another in a way that is hard to interpret. Wormholes, the holographic principle, emergent space-time, quantum entanglement, quantum computers? Nearly every concept in fundamental physics these days makes an appearance, making this subject both captivating and confounding. Thank you for watching, and please hit the like button, subscribe to the channel, and enable post alerts to view more of our future videos. After saying that, keep watching our videos, and I'll speak with you in the next one.